Hi there, physicists. This is going to be lesson 4.6 on refraction of waves. So to get us started, when waves, which can be light, sound, or surface waves, go from a medium of one density to a medium of another density, they change speed and direction. And this phenomenon is known as refraction. Now, right off the bat, you might say, hey, how do surface waves, which are already at the interface between two media, go from one medium to another? Well, in terms of surface waves or water waves, the way that we'll think of it is going from either deep to shallow or shallow to deep. So we'll talk a little bit about surface waves, but primarily for refraction, we are going to focus on light waves. Okay, so our first question is, what happens when waves go from a medium of one density to a medium of another density? And to answer this, I'm going to introduce an analogy of people in a parade holding a banner. So let's imagine that we've got a banner and the banner is going to have some sort of statement. All right, and we're going to have 4 people holding this banner. They're happily marching along, holding the banner. Now, because they're all holding the banner, they're going to maintain a specific distance between each other. And obviously, the movement of one individual is going to impact the movement of another individual. So from a bird's eye view, looking above, what we're going to see is this. We can imagine it as the tops of our people's head and them all holding this banner. So this banner's got a solid wood piece here. That's all of these people are holding on to. Okay, so now let's look at how this helps us answer the question, what happens when waves go from a medium of one density to a medium of another density? Well, let's take this idea of people marching along, and we'll say that they're going to start on pavement, and then they're going to continue this parade, and they're going to eventually march onto some sand. Okay, so we've got row after row of these people holding different banners. And they're being released so that they're all the same distance apart, so that the distance here is the same as the distance here. So these are all going to be the same distance apart, and they're going to have someone here. There's going to be someone timing these people and sending them off in these increments to make sure that they all stay the same distance apart. And there's going to be an infinite number of these banners coming. So they're marching along, and they're going to hit the sand. So as these people come along, they're moving forward, they're going to hit the sand. Well, what's going to happen? Well, obviously, they're going to be able to move faster on the pavement than they are on the sand. So once they hit the sand, they're actually going to slow down. And that means that the people coming behind them are going to be able to catch up. So in effect, the distance between these groups of people is going to decrease. Now, if we think about this in terms of waves, what we have is we have some sort of source here sending out these waves. These are going to act as our wave fronts. So another way to think about these is if we were thinking of these as a sine wave. So if this is our equilibrium point, we're thinking of these as our sine wave, then the tops of the heads are going to be the crest of each wave. So that means then that the distance between these guys is going to be the wavelength. Okay? So the distance between these ones is going to be the wavelength. Now what we'll notice in this example, the frequency is not going to change. The source is going to continue to send out these wave fronts at the same frequency. So frequency will not change. But when our wave fronts hit the interface between the first medium here and the second medium, so first medium here and the second medium here, they're going to slow down. So in this case, velocity will decrease, right? It's harder to walk on the sand than the pavement, so velocity is going to decrease. And we can see that what's going to happen is that our wavelength will also have to decrease. Now that actually makes a lot of sense in terms of our wave equation that we're familiar with, right? So if we hold this thing constant, if we hold frequency constant, well then the only way for the velocity to increase or decrease is for the wavelength to increase or decrease. So we can say that our velocity is directly proportional to our wavelength. So if the speed increases, wavelength must increase. If the speed decreases, wavelength must decrease. Okay, so let's look at a couple of different examples that we could have. We could have our water waves. And as long as these things, actually, because this is a wave, let's draw a ray. We could draw these as wave fronts, but we could also draw them as a ray. Okay, so direction isn't going to change. These guys are all going to hit the sand at the same time. Our marchers are all going to hit the sand at the same time, so their direction won't change. Just their velocity is going to change, and their wavelength is going to change, or the distance between them is going to change. Okay, so this is going to be the same if we've got waves going from deep water into shallow water. We're going to have the same thing. We're going to have these waves come along, and they're going to bunch up on each other. Okay, velocity is going to change. Wavelength is going to change. Frequency is going to stay the same. Okay, and it's going to be the same thing for light as well. So if we're going from a less dense medium, and let's actually just say, let's talk about going from air. So let's talk about light going from air into water, let's say. Okay, so air is going to be less dense than water. So this is the same or the equivalent of going from pavement to sand. So we're going to have the exact same thing again. We're going to have our wave fronts coming in. So now this is light. This is light. And our waves of light are going to again bunch up on each other. So our wavelength is going to decrease, and our wavelength is going to decrease, and our velocity is going to decrease. Okay, so this is consistent among all the types of waves that we've looked at. If we're going straight from one medium to another medium, and what I mean when I say straight is we're going right along the normal line, then what we're going to have is we're going to have our waves slow down if they're going from a less dense to a more dense medium, and their wavelength is going to decrease. Now it's going to be the exact opposite if we reverse these things, so that we said now we're going from water, light's traveling through water, and going into air. So now we're going from the more dense to the less dense medium here. So we're going from the more dense to the less dense now. We're going to see that, well, our waves are actually going to speed up over here. They're going to speed up, and our wavelength is going to increase. Okay, so coming back to our wave equation here, that makes sense. We already said these things are directly proportional, so if our speed increases, our wavelength has to increase. Okay, now what happens though? This is the case where we're going straight. Our waves are coming straight at a medium. What happens in the case where we're going, and let's take light again. What happens when we come at an angle? So what happens when our wave fronts, and we can draw them as wave fronts like this, or we can draw them as rays like this. What happens when these things come in and meet the interface at an angle? Well, we're going to see that they actually, relative to our normal line, which is always, again, always perpendicular to our surface, so in this case perpendicular to our interface, our waves are going to bend. And again, if we take this as our example of our marching band or our parade banner holders here, we can think about it in very simple terms. Well, what's going to happen? Who's going to hit? Which one of our marchers is going to hit the interface first? It's going to be this guy here. And he is going to slow down. That means that all of these ones that haven't hit the interface yet are going to start to catch up to him. So that means that it's going to bend toward our normal line. Let's make it even more pronounced than that. We're going to bend toward our normal line. Our top guy is going to slow down. Our bottom guy is going to speed up. And so we're going to bend towards our normal. Now, again, just like we've seen before, this here is going to be our angle of incident. And this one here, this is going to be our angle, not of reflection this time, but of refraction. Okay? So we can come down and ask this next question. Can we predict which direction waves will bend and how much their speed will change? Well, let's have another look. And again, I said we'll focus mostly on light here, so let's focus mostly on light. So we just saw this case where we had light going from air into water. And we could picture this as our marchers coming along. So we said that our top marcher here is going to hit and slow down. That's going to allow the other ones to speed up and catch up. And we're also going to decrease the wavelength between the first marchers that hit and the ones coming behind them. So now we can draw our ray coming in here. Okay, and we can draw our normal line. And we can see that angle of incidence is going to be greater than our angle of refraction. And so a way to say that is our angle of incidence is going to be greater than our angle of refraction. Or we could also say that our light is going to bend towards the normal. Bend towards the normal line. Now, actually, I've drawn this one. This one again should have been just like the one I drew right down here, where it actually should have been on this side, sorry. Because this is the exact same situation. So in this case here, where we've got light going from air, a less dense medium, to water, a more dense medium, our angle of incidence is going to be greater than our angle of reflection. Another way to say that is that our light is going to bend towards the normal line. And again, we can think of this in terms of our little marching banner holders. Now, let's do the opposite. We're going to take light, and we're just going to reverse. We're going to reverse the situation here. We're going to go from water into air. So we're going from a more dense medium into a less dense medium. So again, let's come at the same approach angle. We'll think of it in terms of our little marching banner holders. Okay, now when these guys hit the interface, again, this one's going to hit first, and he's going to start to go faster. So he's going to start to go faster. These ones down here will not have hit yet, so they're going to go slower. So he is going to start to come around this way if we think of it as a rotation, because they're holding the stick. He's going to start to come around this way. So we're going to get this case. Again, our wavelength is going to decrease. Oh, sorry, it's not the case. When we're going to a less dense medium, our wavelength is going to increase. Okay, so if we draw our normal line in here, which is going to be perpendicular to our interface, and then we can draw our incidence angle here, and we can draw our reflection. So here, and I should have drawn this up in between these guys. Okay, so our angle of incidence here is going to be greater than our angle of refraction here. So in this case, our angle of incidence is less than, so our angle of incidence is less than our angle of refraction. And another way to say this is that our light is going to bend away from the normal line. Okay, so now we've got both of these situations where we're going from our less dense to our more dense medium. So we're going from less dense to more dense here, and we're going from more dense to less dense, and we get some phenomena that are constant across all different types of waves. Whenever you're going from less dense to more dense, your angle of incidence is going to be bigger than your angle of refraction, and you're going to bend towards the normal line. When you are going from a more dense medium to a less dense medium, you are going to have an angle of incidence that is less than your angle of refraction, and you're going to bend away from the normal line. Okay, And we can see some relationships now when we're talking about bending away from the normal line. So we can say that because we know, going back to our wave equation, because we know that our velocity is going to be directly proportional to our wavelength and our frequency is going to stay the same, we can say that the fraction of our velocity has to be equal to fraction of our wavelengths. They have to change, they're directionally proportional, they have to change by the same value. And from experimentation, we also know that the sine of the angle of incidence, so the angle in the first material is going to be proportional to the sine of the angle of the refractive. And all of these, we can use any of these to figure out what we call the index of refraction, n, which is the index of refraction for any material. Okay, so the index of refraction for light especially, so we're going to be especially interested in light, is another way to describe this is that how much slower light is traveling in water versus air. So because actually, let's introduce another relationship. Because the speed and wavelength of light are difficult to measure, we use this equation actually, which is the index of refraction for an object is equal to the speed of light divided by, so this is speed of light in a vacuum. This is speed of light in a vacuum over the velocity or the speed of light in the medium. And that will give us the index of refraction for that medium. Now, what's interesting is that for air, our index of refraction is 1. And what is this actually telling us? Well, for this to be 1, it means that the speed of light in air has to be very close to the speed of light in a vacuum. So air doesn't really slow down light much. I believe it's actually for air it's 1.0003, I believe, is the index of refraction. So light is going almost as fast as air as it is in a vacuum. We can take any other material though, or medium now, and we can say, well, what is the speed of light in a vacuum? And comparatively, what is the speed of light in that material? And that will give us the index of refraction. So there's all sorts of tables on the index of refraction. We'll have a look at those later on. And in some of the questions, you'll get an index of refraction or a table of indices of refraction that you have to use to solve some problems. But this is what we're figuring out. So we want to know how much slower. So in this equation, we're figuring out how much slower or what fraction is the speed of light in the object versus the speed of light in a vacuum. Now, another equation that we can use in other general cases is Snell's law, where we have the index of refraction in the incidence material times the sine of the angle of incidence is equal to the index of refraction in the refracting material times the sine of the angle of refraction. And again, here we'll be given 3 and we'll be asked to isolate either one of the indices of refraction, or we'll be asked to figure out the angle in either the In this case, we could be asked to figure out the angle of incidence, or we could be able to figure out the angle of refraction over here. Okay, so to answer our question up here, can we predict the direction waves will bend and how much their speed will change? Well, yes, we absolutely can, because now we have all of these handy relationships to say, and we can figure out how much the speed will change. We can also figure out the index of refraction for any medium, and based on our marching band or our marching banner holders, we can also predict which way is the light going to bend, either towards the normal line or away from the normal line. Okay, so we can predict now, is light going to bend towards or away from the normal line? So now we can ask an interesting question, and we can say, what happens if we continue to increase the angle of incidence? Well, when we're going from a more optically dense to a less optically dense medium, and only in this case when we're going from more optically dense to a less optically dense medium, a critical angle can be achieved. And this is important, a critical angle can be achieved where the angle of refraction is 90 degrees to the normal line, i.e., in other words, it means it's going to be going directly along the surface. In this case, no light is refracted. So let's have a look at what we're talking about here. So again, we can be talking about light, and we can be talking about going from, now we have to go from more dense, so we're going to go from water, and we're going to go into a less dense medium. So let's talk about going into air, and we'll draw this as a ray diagram. So let's say we're coming in at this angle of incidence. Now, again, from what we just talked about, are we going to bend toward or away from the normal in this case? Well, if we go back up to what we just talked about, we said when we're going from more dense to less dense, we're going to bend away from the normal line. So we can actually have an angle, and it would probably be a little bit steeper than that. We'll have an angle, though, where we're coming from a more dense medium, we hit our interface, and our angle of refraction is going to be 90 degrees. This is the critical angle. So this angle of incidence is the angle that we have to hit to have our angle of refraction be 90 degrees to the normal. So that would make this the critical angle. So we can be asked to find now, what is the critical angle of the interface between two mediums? And we can take this one step further. We say, well, what if we have that exact same situation? Let's do this down here. What if we have that exact same situation with light traveling from water into air, and we increase that angle even further beyond the critical angle? Okay, so now we've increased this even further. Well, what we're going to get in this case is it's going to bounce off the surface, and all of our light is going to be reflected. So now this is reflection. This is what we call total internal reflection. Okay, so importantly, when we've got our critical angle, when we achieve our critical angle, no light is refracted. Okay, so when we achieve our critical angle, no light is refracted. And if we go beyond that critical angle, we're going to get what's called total internal reflection, where all of the light is reflected back into the more optically dense medium. So in this case, we're going to go back into water. Now this creates a cool illusion, like with the sea turtle here. Based on the angle that you're seeing this sea turtle at, so if we draw what's going on here, you have your turtle, and you have you observing the turtle. What you have is all of the light coming from the turtle is being reflected. So your angle of incidence, oh, that's not your angle of incidence, is it? Let's draw our normal line. Your angle of incidence here is equal to your angle of reflection here. So you are actually, the surface of the water is acting like a mirror here. So you can actually see the reflection of the turtle in the surface of the water. Okay, so to wrap up here, let's go back and we can talk about, okay, we used our people holding our banner marching in a parade analogy to talk about what's going to happen when waves go from one medium to another. When they go from a less dense to a more dense medium, they're going to slow down, and that means that the wavelength is going to decrease. When they go from a more dense medium to a less dense medium, that means they're going to speed up, and their wavelength is going to increase. We also said that if they approach at an angle, we can predict how they're going to move. They're either going to bend towards the normal line, and that's going to be in the case when we're going from the less dense to the more dense medium. We're going to bend towards the normal line, and our angle of incidence is going to be greater than our angle of reflection. Or if we're going from a more dense to a less dense medium, we're going to bend away from the normal line, and we're going to have an angle of incidence that is less than our angle of refraction. We also had a look at these handy relationships that we're going to be able to use. We said that our index of refraction is going to equal the velocity in our first medium over the velocity in our second medium, which is equivalent to the wavelength in our first medium to the wavelength in our second medium. And also from experiment, we know that it's going to be the sine of the angle of incidence over the sine of the angle of refraction. We also said that we can figure out the index of refraction of a medium by saying, what is the speed of light in a vacuum? How fast is the speed of light in that medium? And the fraction of those is going to tell us the index of refraction. We also said that we can use Snell's law, and again, we'll see this below in more general cases where we can have the index of refraction in one medium and the sine of the angle of incidence, and that's going to be equal to the to the index of refraction in the second medium times the angle, sine the angle of refraction. Okay, we also said that if we're going from a more dense to a less dense medium, there is an angle that we can hit called the critical angle, where our angle of refraction will form a 90 degree with our normal line. That means that no light is being refracted. And finally, if we go beyond that, if we increase our angle of incidence beyond that, we're going to get total internal reflection. Now, it's worth mentioning, just as we wrap up, to say that whenever we have refraction off of a surface, so at an interface here, we're almost always going to have a little bit of reflection as well. So some light is going to get reflected. A little bit of light is going to get reflected. Most of it will be refracted. But in the case of total internal reflection, no light is going to be refracted. Okay, so what are some scientific uses for refraction? Well, anything that uses a lens, microscopes, telescopes, cameras, projectors, anything with a lens, is taking advantage of refraction, right? And we looked at this with mirrors. We can say the same things with lenses. If we have a convex lens and we have light coming towards it, we know that that is going to bend the light. Okay, so it's going to bend the light. And we're going to get some refraction. Refraction in nature, we can have rainbows are an example of refraction. It's light refracting in raindrops. Our eyes have a lens in them, so they're going to refract light, but they also have a liquid in behind your lens called the vitreous humor, which is going to, again, refract light because it's going into a different medium. And we can talk about the position of organisms in water. So let's have a quick look at this last one, the position of organisms in water, because this is one that you can test out at home. So if you've got some water here and you have an object, so let's draw our water, and you have an object sitting in your water, like a pencil. So you've got a straight object here, and you are looking into your water. What's going to happen is you're going to have light coming from your object, and when it hits the surface, it's going to refract, and in this case, we're going from our water to air, so we're going to a less dense medium. We're going to bend away from the normal. And what our eye is going to do is it's going to trace that back as though there was no refraction. So it's going to trace this back as if there was no refraction, and it's going to meet at a point here, which is slightly higher than the actual object. And so what that's going to make it look like is it's going to look like your pencil is bent. And you can try this by sticking a pencil into a bowl or a cup of water, and you'll see that the pencil appears to be bent. Okay, we're going to move on, and in another video we'll have a look at some of the problems with, or some of the practice problems with refraction.